And so, the first speaker is Thiago Castilho de Mello, and he will talk about images of multilinear polynomials on upper triangular matrices. Please, Thiago.
Thank you, Artem. First, I'd like to thank the organizers, Artem and Alexei, for the invitation to give this talk. I'm going to talk about this subject of images of polynomials on algebras, and more specifically, images of multilinear polynomials on upper triangular matrices. Okay, so first I will motivate this kind of problem and give present some results which are known about full matrices and other algebras, and in the end I will present our result on images of multilinear polynomials on upper triangular matrices. That is a joint result with Ivan Gonzalez Bergante. Okay, well, I like to start this with this to motivate this problem. I like to talk about this theorem of Schroeder, Albert, and Lukenhaupt. Before that there is this simple exercise of linear algebra that is to show that if you consider two matrices A and B, when you consider the commutator, the trace is zero. Okay, here the commutator, of course, everyone knows. I'm just writing here. Is AB minus BA. Of course, the trace of this is zero, but the interesting thing here is that there is a converse for this fact. That is, if you consider an arbitrary matrix of trace zero, it can be written as a commutator of two matrices. Okay. Actually, it's simple to show that any trace zero matrix is a linear combination of commutator, but to show that it is only one commutator, it's a little bit less simple. And this is another result of Schroeder in the 30s, and in the case of characteristic zero. And for arbitrary characteristic, it's a result of Albert and Lukenhaupt in the 50s of last century or millennium. But we can read this result in a different way. This result is saying that if you consider the map that take a pair of matrices and take it to the commutator, this result, this theorem says that the image of this map is the set of trace zero matrices. Okay? But then I can consider, instead of considering this commutator, I can consider another polynomial. For instance, consider a polynomial P here in m variables. And by fx, I'm denoting the free associative algebra, freely generated by this set x here. So consider a polynomial in m variables. It defines in a natural way this map, which I'm also denoting by P, that is the evaluation of P in the matrices A1 up to AN. Okay? So the natural question is, given a polynomial, what is the image of this polynomial? Or what subsets of here can be given, can be the image of some polynomial P here? So this kind of question was attributed to Kaplansky. You will not find any paper of Kaplansky where he explicitly write this question, but it was, people say it's from Kaplansky. And we are going to explore this a little bit more, okay? So we want to consider this kind of problem. Given a polynomial, what is its image? For which subsets here are the image of some polynomial? And later I will consider the case in which the polynomial P is multilinear. What can we say about the image of a polynomial when it's multilinear? Okay, let's see some examples to start understanding this kind of problem. So the first example is very simple. It's a polynomial in one variable. Of course, the image is the whole algebra. Okay, the full algebra, full matrix algebra is the image of this polynomial. It's a trivial case. Another known result here is that this is a polynomial identity for K by K matrices. So if it's a polynomial identity, any evaluation of variables by matrices will result in zero. In other words, we are saying that a polynomial is a polynomial identity is the same as saying that the image of such polynomial is 0. Okay. Another example here is the one I have already mentioned, that the image of the commutator is the set of 3 zero matrices, and here for 2 by 2 matrices we can consider this polynomial, and the image of this polynomial is the set of scalar matrices. This is a central polynomial. Okay. By central polynomial, I mean a polynomial which takes only values on the center of the algebra. So I'm identifying here the center of the matrices with the field F. Okay. Here, this example is for 2 by 2 matrices, but we know that there are examples of central polynomials for matrices of arbitrary order. So we could consider here another example for any matrix of any order. Okay. So these are some examples of sets which can be realized as image of some polynomials. Okay. Okay. And we can see here also that polynomial identities and central polynomials are related with this kind of problems of determining image of polynomials. Okay. Okay. So if you want to determine the image of a polynomial, it's interesting to know what structure this set has. Okay. So the first proposition here says that if we consider an arbitrary polynomial, the image of such polynomial is invariant under conjugation. Well, how can we see that? Well, an element of the image is something like that. Okay, so if you conjugate this by a matrix, we need to show that this is the image of some polynomial too, of this polynomial evaluated in some matrices. Okay, but P is nothing more than a linear combination of monomials. So when you conjugate this P by this matrix B, we are doing this for each monomial. So we get this, but we can put B minus 1, B minus 1 in the between each pair of matrices here. So we are going to get this. Oh, sorry. I missed the B minus 1. Okay. So when we do this for all monomials, actually, we are showing that this is the same as evaluating the polynomial P in the conjugation of the matrices. So we are still with an element in the image of a polynomial. So this is the first important fact about images of polynomials. Later, we are going to consider the case where the polynomial is multilinear. When the polynomial is multilinear, of course, it's invariant under scalar multiplication, because you can change the variable by this scalar multiplied by this variable. Okay. So actually, it doesn't need to be multilinear. You can consider only that it's linear in one variable, for instance. It's enough to consider the fact that it's invariant under scalar multiplication. But then the next question will be, if we consider two elements in the image, A and B, are their sum still in the image? That's the question. If A and B are in the image of a polynomial P, is the sum A plus B in the image of P? With this, we are asking if these two things together would be the question of, is the image of a multilinear polynomial a vector space? So this seems to be a naive question, showing that something is a vector space is usually exercises of linear algebra, basic linear algebra. But now it's a very more difficult problem. So this question is attributed to Lvov. Actually, this you can find, it's not attributed, it's a question of Lvov. You can find it on the Dinster notebook of unsolved problems on algebra. And we are going to develop a little bit more to relate this with other results here. So If you want to, if you want to show that the image of P is a vector space, it would be the same as the linear span of it. Okay, the linear span of a vector space is itself. So let's consider the linear span of the image of a polynomial, and let's see what we get. So the first proposition is saying that the linear span of the image of a polynomial is a Lie ideal of K by K matrices. This is not simple. This is also simple to show this is true, because what do we mean by Lie ideal, right? It means that if you consider an element there and you do the Lie product, that is a commutator, by any matrix B, we are still in the image of P. Okay? And again, to prove this, you go to the monomials of P. So, because when sorry, not the image of P, but the linear span. Okay? The linear span of the image of P. And to prove this, it's simple as the case before, because you go to the monomials, and when you do this with the monomial, here is the product of K matrices, and do the commutator with B, it's the same as doing this. So this is when putting all these monomials together, this is the same as a sum of P evaluated in some things like this. Okay, so there a sum of elements which are in the image of P. So this lies in the vector space generated by the image of P. Okay, so it's a Lie ideal, and the Lie ideals on matrices were described by Hairston. Actually, at least in the case of infinite fields, he showed that the only Lie ideals we have here are these ones. That is the set of the whole algebra, the set of trace zero matrices, the field which we are identifying with the scalar matrices, and zero, of course, the trivial one, right? And so if we put these two things together, we have that the linear span of the image of P must be one of these. So if the linear span of the image of P is the image of P itself, that is the conjecture of the problem of Lvov, the question of Lvov, then it would be one of these. So we have now what is known as Lvov-Kaplansky conjecture, that the image of a multilinear polynomial P evaluated on matrices must be one of these four possibilities. Okay? And if we come back to the examples we discussed before, these are exactly the examples I showed. The full matrix, algebra, zero, trace zero matrices, or the field, the set of scalar matrices. Okay? Let's see what happens if we consider a polynomial which is not multilinear. So we're going to consider this example here. P of x is x to the k. A polynomial only one variable. Okay? And we're going to evaluate on this and show that it's not a vector space. Well, when we evaluate this on these matrix units, EII, here, of course, EIJ means we have one in position ij and zero elsewhere. So when we evaluate in EII, these are idempotent, so we obtain EII itself. And when we evaluate on this for I different from j, we again obtain this. Okay? So this is in the image, and this is in the image. So if you consider the linear span, the difference is in the image. So the difference of this is this one. So in the linear span, we obtain all matrix units, which are bases for K by K matrices, so it generates it as a vector space. Okay? So the linear span of the image of this polynomial is the whole algebra. And now we are going to show that this guy here is not in the image for I different from j. If it's in the image, it would be written this way for some matrix K, because the polynomial is this. Okay? But this one is nilpotent, so A would be nilpotent. But the nilpotent index of a matrix here is bounded by K. So A to the K would be 0, and this would be 0. That's a contradiction. So this is not a vector space. Okay? So this is just to show an example of a polynomial whose image is not a vector space. Okay, but let's go back to the case that the polynomial is multilinear and see some positive results in this direction. So the most important result in this direction is this, that for 2 by 2 matrices, Canabelov, Malev, and Rowan showed that if P is a multilinear polynomial evaluated on 2 by 2 matrices, then the image of P is one of those possibilities. So they prove the conjecture, but they have a restriction on the field. It must be or quadratically closed or the field of real numbers. For arbitrary fields, what they obtained is that the image is either 0 or F. I mean, it's a polynomial or identity or a central polynomial, or otherwise they just he just proved that the image contains all trace zero matrices. Okay, but we still don't know if it's a vector space or not. Okay. Also, for 3 by 3 matrices, they have some positive results showing a list of possibilities of the image of such polynomial. But the problem here is that there are some cases here which are not necessarily subspaces of 3 by 3 matrices, but these cases, which are not subspaces, have not been realized as the image of some polynomial. So the problem is still open even for 3 by 3 matrices. Here they have some types of subsets here. I will not enter into these details, okay? But just to show that there is a finite list of possibilities here. The case n equals infinity, that means that we are considering the algebra of endomorphisms of an infinite dimensional vector space over a division algebra D. And this was shown to be, the image of a multilinear polynomial here was shown to be a vector space. This is the result of Vitas. Okay. For polynomials of degree 3, Dickham and Clapp considered over the complex numbers. So for polynomials of degree 3, they have an interesting result, but not complete. They show that for matrices of even order, the image is a vector space. And for matrices of odd order, it's a vector space only for small odd numbers, okay? For k greater or equal than 17, they didn't show this is true. So the problem is still open for polynomials of degree 3 and matrices of arbitrary order. Okay, so this was some results concerning images of polynomials evaluated on full matrix algebras. But now we can consider some variations of these problems. For instance, you take an algebra A, here an associative algebra or a Lie algebra, Jordan algebra, or some algebra in your favorite variety. Consider a multilinear polynomial P. And multilinear here means multilinear in the free algebra of your variety. And you can ask if the image of this polynomial is a vector space. Okay, and I'm going to mention some results in this direction, which are not considered over matrix algebra, but other, not necessarily associative algebras. Here, for instance, when you consider the image of a Lie polynomial on SL2, they show that the image is SL2 or 0, or the set of trace 0 non-important matrices. For Lie polynomials of degree up to 4, the image is always a vector space when evaluated on trace 0 matrices and these other classic simple Lie algebras. So for polynomials of low degree, it's true. Also for the Jordan algebra of symmetric matrices, here, polynomials of degree 3 are have image as vector spaces. And some other interesting results here for the quaternion algebra and for the octonion algebra. Here, they show that the image of the polynomials are either 0, when they are polynomial identity, R, that means the central polynomial. Here, V means the set of quaternions with real part equal to 0, okay? Or the whole algebra. And the same result for the octonions. The difference here is that for octonials, we need to consider non-associative polynomials. Also, in the setting of Jordan algebras, they proved that for this algebra they call JN, that actually is the algebra of the Jordan algebra of a bilinear form, which is also simple. They show that the image of a multilinear polynomial is also a vector space in a similar way as before. Either 0 when it's a polynomial identity, R, the real numbers, where R means here the set of the subspace generated by the identity, or the set of pure elements, that's the subspace generated by these other basic elements of our algebra, or the whole algebra. They are very similar results. Always we have these 4 possibilities, and they have either dimension 0 or 1, or codimension 1 or 0. The dimension or the codimension are 1 or 0. Okay, and we can see that the case of simple algebra seems that to be the case where the conjecture, the variations of this conjecture are valid. So we have this generalized Levov-Kaplan's conjecture that says that if F is a field and V is a variety of F algebras, a polynomial which is this P must be multilinear. The image of a multilinear polynomial in a finite dimensional simple algebra is a vector space. Okay. Actually, there are still results for the case of infinite dimensional simple algebras. For instance, the Weyl algebra, the image of a polynomial which is multilinear on the Weyl algebra is a vector space. Actually, it's the whole Weyl algebra, if the polynomial is not 0. Okay. And some other results, but now for non-simple algebras. Here is a result of myself with Fagundes. We show that we consider the image of polynomials on upper triangular matrices. Okay. And we show that for polynomials of degree 4, up to 4, the image is a vector space and one of these. So the whole algebra, the Jacobson radical, or the square of the Jacobson radical. Here, the Jacobson radical, I mean the strictly upper triangular matrices, the set of matrices which have 0 in the main diagonal here. Okay. Okay, in the same paper, we proved that the linear span of the image of an arbitrary multilinear polynomial is some power of the Jacobson radical. Yeah, so the result was for polynomials of degree 4, up to 4, but when we consider the image of the polynomial, but when we consider the linear span, we proved this. So we have conjectured that not the linear span, but the image of a polynomial which is multilinear evaluated here would be this for some r. And this is the result I'm going to show you today. Okay, it's interesting to mention also that Fagundes considered the problem of the image of a polynomial on J, on the strictly upper triangular matrices, and she showed that the image is either 0 when it's an identity, or J to the m here. This m is exactly the degree of the polynomial. Okay, in particular, it's always a vector space. So we are going now to consider the image of a multilinear polynomial on Utn for an arbitrary n and for polynomial of arbitrary degree. So to that, we need to introduce some ideas here. And first, we are considering this descending chain of T ideas. So recall that the polynomial identities of this algebra are well described, are well known. They are described. Sorry. And these are exactly the product of the T ideal generated by the product of n commutative. So any identity is, in some sense, in the sense of polynomial identity, a consequence of this polynomial here. Okay? So we're going to consider this chain of T ideals. So we have the free associative algebra, the T-ideal generated by one commutator, the T-ideal generated by the product of two commutators, generated by the product of three commutators, and so on. And any polynomial here will be in sum of this. Okay? And for any polynomial f, there exists an integer r such that f is in the T-ideal generated by the product of r commutators and is not in the T-ideal generated by the product of r plus one commutator. So when this happens, we are going to say that f has commutator degree r. Okay? Okay, so since we know that this is the set of identities of UTR, and this is the set of identities of UTR plus 1, this is the same as saying that f has commutator degree r if and only if it's an identity of UTR and is not an identity for UTR plus 1. Okay? The idea here to prove our result is to first give a characterization of multilinear polynomials which have commutator degree r in terms of its coefficients, and with that show that the image is a vector space. Okay, so any multilinear polynomial can be written this way. Okay, so it's uniquely defined by these coefficients here, which are in the field. So they are indexed by elements of the symmetric group. And we can show that if you have an unitary algebra, then if the sum of these coefficients is non-zero, then the image is the whole algebra. Okay? It's simple to prove this because you can consider the substitution of any variable by one, except the last one that we evaluate by a matrix M divided by the sum of coefficients, which is non-zero. Okay? So since these guys here commute with themselves, such evaluations, all evaluations independent of the order, will result in this matrix. So this will be the sum of alpha sigma multiplied by m over the sum of alpha sigma. So this cancel out, and you obtain the matrix M. So for an arbitrary matrix M, you can find an evaluation which obtain M and the image of F. Okay? So these conditions give that the image is A. And if the sum of the coefficients is 0, we can show that this is equivalent to say that F is a polynomial which is in the T-ideal generated by the commutator. If we recall that the definition of commutator degree, this condition 2 here is just saying that just giving a characterization of polynomials of commutator degree 0. I mean, polynomials which are here and are not here. They are exactly the polynomials which have the sum of coefficients different from 0. Okay? So this gives a characterization of multilinear polynomials of commutator degree 0. Can we do the same for multilinear polynomials of commutator degree r? A characterization in terms of its coefficients. Of its coefficients. Well, yes, we can. It's a little bit technical, but I will try to explain you. What are we doing here? So we are considering a polynomial in m variables, 1 to m. And so we are going to partitionate this set this way. We fix an integer k, and we consider k subsets here, which disjoint subsets here, and another subset here we are denoting this way. Okay? So when we fix k, when you consider this capital T's, I'm going to denote these guys by T. And I'm going to denote these by T, small t. When you consider this this defines the partition we're considering, okay? So for each k, you consider these two elements of the partition here, and we define with it the set of all permutations which satisfy some conditions here. What are these conditions? I'm going to explain it. So let's write the elements from 1 to m in order. So we are going to have 1, 2, and so on up to h1. Which is h1? Is 1 less than the size of t1. Okay? Then h1 plus 1, h1 plus 2, and so on, until h1 plus h2, and so on. We are going to consider these blocks of elements here. So I'm going to erase this and write this again. So we have this first block, then we have h1, another block, h1 plus h2, and so on, until h1 plus hk. Okay? And we are considering this set here, that is a subset of the permutations of n elements. What are the which are in this subset? These are the permutations which send any element here for this first part of my partition, and send this h1 to this first element here. Then the second part of my partition to this t2, which is here, and this h1 plus h2 to the second element which appears here, and so on. This will be going to tk. Okay, so I'm considering all permutations of Sm which make this, we do this job here with these restrictions. Okay, and we are considering, why we are defining these guys, because we are considering this coefficient here, which is the sum of all coefficients indexed by permutations which are in this SKTT. Okay. Why this is important? Because with that we can prove, we can characterize polynomials of commutator degree R. So consider a multilinear polynomial. So it has commutator degree R, this integer R, if and only if these coefficients we have just defined are zero for any choice of capital T and small t when k is smaller than R, and there is some choice of capital T and small t when k is equal to R that is non-zero. So these two conditions characterize the multilinear polynomials which have commutator degree R. Okay. Well, and how can we prove this? This is based on these two lemmas that show that if a polynomial, a multilinear polynomial, satisfies the first condition, that is, all these beta are zero for any choice of capital T and small t, all those partitions we consider, when the number of parts here is less than n. If these are all zero, we prove that it's an identity. And the other lemma is that for this exactly n, if there is some t and t, capital T and small t, which this coefficient is non-zero, then we can show that f is not an identity. Okay, so these two lemmas together give that theorem that we put here with that other condition we mentioned before. So these are equivalent. F has commutator degree R if and only if it's an identity of this and it's not an identity of this, if and only if all those coefficients are zero for k smaller than R, and some coefficient of this type is non-zero for some choice of, for some partition when you consider the number of parts being R. Okay? Okay, and with that, we were able to prove that the image of an arbitrary multilinear polynomial on upper triangular matrices is exactly J to the R, where R is the commutator degree of the polynomial. And here, of course, we have the restriction of the field being infinite. Okay, I will give an idea on how this is true using that idea of not an idea, but I will mention how we were able to prove this using that idea of commutator degree. So if the polynomial has commutator degree R, so these guys are all zero for k smaller than R, and some of this is non-zero. Okay, so we choose this guy which is non-zero, this choice of R, capital T and small t, such that this coefficient is non-zero, and we are going to consider a specific evaluation of these matrices. what we are going to do. These matrices here, all matrices which are here in the first part will be evaluated to a diagonal matrix D1. All matrices here will be evaluated on a diagonal matrix D2. And so on. These matrices which are in these blocks will be evaluated to the same matrix D1, D2, and so on. Okay. The idea here is that doesn't matter the order these guys are sent here to T1 is exactly this, because diagonal matrices commute, so it doesn't matter for us the order, but we will consider the sum of these coefficients. Okay, and the other evaluations we are going to do is to evaluate these guys here, actually these guys here, the variables with index T1 to a matrix of this form and 1. Let's write it here. And I would be will be a matrix with zeros on the main diagonal, of course zeros here, and here we are going to put variables y1 up to y k minus 1, indexed by I here, and 0. So the only non-zero entries are in this entries above the main diagonal. Okay, so these matrices here will be evaluated on this. Okay, and the last one, at least except for the last one, that will be evaluated on a generic matrix. When we do these evaluations, considering the fact that some of these coefficients is non-zero, we are able to solve the equation f evaluated on these matrices is equal to a given matrix in the rth power of the Jacobson radical. So now it involves a lot of computations and some more difficult steps that I'm not going to show here, but that is the idea on how we can use this to prove the theorem. Okay? And the infinite field is used because at some point we need to evaluate a polynomial in commuting variables and obtain a non-zero result. So this is why we use the infinite field here. Okay, so this was proved also by Lu and Wang independently with different methods, but their proof holds for fields not necessarily infinite, but big enough. Okay. Just to finish here, we mentioned the idea of commutator degree, but we could also consider another chain of the ideals. For instance, this is an important chain of the ideals here. That's the chain of the ideals generated by the standard identities. Is it possible, the question I do here, is it possible to characterize the elements which are here, for instance, and are not here in terms of its coefficients? I think this would be, I think this may be really, really difficult. I haven't tried it, but I think it could be really useful to study identities on matrices. And just let's hear for if someone has some idea or want to try to solve this. So that's it. Thank you very much.
Okay, thank you for your talk. Are any questions, comments? Okay, then I have one question. Well, I have two questions actually. So correct me if I'm wrong, but now there is no any counterexample to the conjecture that for any simple algebra, its multilinear image is a vector space. Is it correct?
Yes.
Okay, but if algebra is not simple, then do we have some like counterexample?
Yes. There are some examples for on incidence algebras, that are some subalgebras of upper triangular matrices, in which some, I believe
yes. Incident algebras. Yes, I remember.
Yeah,
Yes.
there is an example where the product of two commutators is not the image is not a vector space. This was presented by Felipe Yukihide. I'm not sure it's matrices of order 6 or 5. I'm not sure.
I guess 6.
Yes, I guess 6. And later, Hono Jururi also gave me a smaller example. But
in case algebra is simple, its image can still be always vector space. Yes, even in case algebra is not associative.
Yes. For example, the examples ones are always vector spaces. The polynomials of low degree on some simple Lie algebras, on Jordan algebras, on the octonials. All these are examples where the image is a vector space. We don't know what
And so my second question is about the case when the image is not vector space. It's, of course, when polynomial is not multilinear. For example, this basic example, x powered by n, yes, which you showed me, and where image is not a vector space. But can we say something about this image? Like, is it a fine variety, for example, or... I mean, okay, it's not vector space. Maybe it's a fine variety. Maybe it's something else. Something which has been studied.
Sorry, I didn't understand. If it's not a vector space, you want to know what?
Yes. For example, consider this particular case. We have polynomial x powered by n, yes, and we have matrices. Image is not vector space, yes? But maybe it's a fine variety. Can it be a fine variety?
I don't know, but I believe so. I believe it can be. But I don't know.
Formulated, I don't know, maybe it's trivial conjecture that image with respect to any polynomial, let's say it's always a fine variety, or maybe not a fine variety, some other kind of variety, or some other set with some structure, let's put it this way.
Yeah, but I don't know. In such generality, I don't know the answer. I believe there is not an answer.
Okay, so any other questions? Well, I do not see it. Okay, then thanks again for your interesting and detailed talk.
Thank you.